So hello everyone and welcome back to this next lecture in the DC to DC converter series where we've been simulating the transformer. So this is where we had left off in the previous lecture where we had simulated a transformer with a step down ratio. So just a recap, we had simulated a 2:1 transformer, so a step down transformer, and we had seen that we had indeed achieved this 2:1 ratio. So the blue line is the primary voltage, the yellow or orange line is the secondary voltage, and we do see that the secondary voltage is half the primary voltage, right? So we will continue with this analysis, a little bit of analysis in this lecture related to this. So as before, as usual, before I start the lecture, a little bit of brief background that if you are interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses on the MOOC website Udemy. This is one of the first courses which I have developed, which is simulating power electronic circuits using Python. And in this course, I talk about installing the software, installing Python power electronics, some basics of power electronics and basic electrical engineering, and finally, a case study of simulating a buck converter. If you are interested more on the signal processing side, I do have another course which is basics of digital signal processing for power engineers. And in this, I talk about the basics of signal processing, which includes Laplace transform and discretization. And finally, there is a case study in which I use frequency response characteristics using NumPy and SciPy to design a low pass filter and a notch filter. And the last course, which is the latest course and which is probably the most relevant for these last few lectures, is simulation of magnetics for power electronics using Python. And in this, I talk about how we can use Python power electronics to simulate an inductor, coupled inductors, and also a transformer. And I have a case study in which I have a flyback converter, which is a high frequency transformer with multiple windings. Right? So the link for these courses is provided in the description for this video. So if you're interested, please do check it out. So coming back to the lecture, we had created only one plot where we had looked at the transformer windings. So like for example, we had plotted the primary winding voltage versus the secondary winding voltage, right? Now, in this next lecture, let us now plot the currents as well. So before that, let me go and plot it again, because we might have a few more cycles than last time. So this is it. So as you can see, the simulation is stable, and you'll see that the blue line is still double the value of the orange line, which means that we do have a stable 2:1 step down transformer. So let us now continue and check out the currents. So first and foremost, let me go over and check out what else we have. We have the source voltage, right? Now the source voltage has this ammeter SRC, and at the same time we also have the load, which is here. It has a load current. So let us plot these two and compare them. So let me add a plot, and I will call this transformer currents. The name of these plots is totally up to you. And let me plot first the ammeter source. Let's call this I prime, or let's call this I1 rather. And let me plot the load, which is already there, so let me call this I2. And we can click on done. And let me plot this. So these are the transformer currents. So a fairly interesting result, right? Now let's see what's happening here. First and foremost, you will see that, okay, this is the key. So the orange line, right, is the larger one, and the blue line is the smaller one. Now, as before, the blue line is the primary current, the orange line is the secondary current. So if we go back to our code, we see that we have a step down transformer. So the low voltage winding will have the larger current, the high voltage winding will have the lower current. So therefore this plot is perfectly okay, right? The primary or the first winding is the high voltage winding and therefore the current is smaller. The secondary, which is the orange or yellow line, is the high voltage, it is the low voltage line and therefore has a higher current. Now the question you might ask is, what is with this blue line having a DC offset, right? It has clearly a DC offset. Now for that, what we need to do is we need to go and find out what's happening with our actually what's happening with our voltages. Now as you can see here, the voltage is a sine wave, right? It starts at 0, right? If you just go in here, it starts at 0. Now we have already seen that the flux is the integral, right? We are integrating the applied voltage and arriving at the flux. We are now using these flux linkages to calculate the current. Now, if you integrate a sinusoid, you would expect a negative of a cosinusoid, right? Integral sine omega t is equal to minus cos omega t. But when you do this form of integration, numerical integration, it is important to understand that there will be a DC offset. The reason is because our flux linkages starts at 0, right? So let's go back here and have a look. We are seeing that our current is starting at 0, and that is only expected. Why? Because when you apply a voltage to a winding, the current cannot jump, right? We actually are expecting the current to jump because when you have flux linkage, which is a negative cosine, you expect the current also to be a negative cosine, but that is not possible, right? Because the transformer inductance will not allow the current to jump instantaneously. That is the property of a transformer. The inductor will always oppose the rate of, or rather a sudden increase in current, right? So therefore this results in a DC offset. This DC offset is not a bug, right? Whenever you turn on a transformer, there is going to be a DC offset, and this DC offset will decay with time, right? Now what I'm going to do is, let me go over and let me instead change the voltage to do something different. Let me go back here, edit circuit parameters, to the voltage source, and instead of having a sine, so basically whatever I do choose here is sine omega t, right? Now there is also a phase angle, right? There is a phase angle. So if I choose a phase angle of minus 90, now this becomes sine omega t minus 90 degrees, right? Now what that means is that I now have a phase delay, right? Now a phase delay would mean, or rather I should put it to be omega t plus, well, it's sine omega t plus 90 degrees should be what it is, because this is it. So if we have this particular phase angle, we now are simulating a cosinusoid. So let me save this and let me go back and run the simulation. So if I click on the run button, always check if there is an error. There is no error, so we are okay. And let's click on the winding voltages. So let me click on the winding voltages, and we see a very interesting result. As usual, we have some amount of instability. Now I do see I made a mistake. It should have been plus 90 degrees, but anyway, let me just plot it again. It is stabilizing. This is a little worrisome because I do not expect this to jump like this. Anyway, so first thing I'm going to do, I'm going to stop the simulation, go back to the main page, edit the circuit parameters, and just change this to plus 90 so that we have a proper cosine, not a negative cosine. forgot to check if there is an error. There is none. So now we have a cosine. So for example, what I would do, the next thing we need to do, we need to deal with this large instability problem that we are having. I would just go increase this again. Eventually we would have to decrease this time step, but I would rather wait for that because that will only simulate, rather slow down the simulation. Let me go over. There is no error. And now let me plot it again. Yes, it has decreased, or at least it's stabilizing a little faster. The only solution looks like I would have to decrease the time step of simulation. But most importantly, let me go and have a look at the plot of the transformer. And now you see that the DC offset is gone. Right now, this DC offset, which has disappeared, right, is not something which is very difficult to understand. For example, this DC offset is now gone because when we integrate a cosine, you will achieve a sinusoid. But the most important thing is a sinusoid starts at 0 and therefore it is matching with the numerical integration. Right? In a numerical integration, it is impossible to really predict what would be the final, or rather what would be the final result of an integration. Analytically, we can always determine what is the result of an integration, but numerically we cannot. And at the same time, physically, when you apply a voltage to a transformer, the current is always going to start at 0. And if the current starts at 0, the flux linkage also starts at 0. This implies that you will have a DC offset. Now, because we have a cosinusoid, by sheer luck, we do not have a DC offset because our integration is such that it starts at 0, right? So this is a special case. So let me go back and run a few more cycles of both the voltage and the current. And let me go and check out the result. So you see that the results are stable. The blue line is indeed double the value of the orange line, which means that the primary voltage is double the secondary voltage, and we have a step down transformer. So let's go and have a look at the transformer currents. And in the transformer currents, we see also that the primary is actually primary is almost half the secondary. So now the question is, what makes this different, right? Why do we not see a complete half? Let me go and zoom in a little. So let me zoom in between 0.3 and 0.35. So, as you can see, our primary current, which is the high voltage winding, is the lower current. The secondary current, which is the low voltage winding, is the higher current, which is expected. Now, what is a little puzzling is the fact that we do not have the 1:2 ratio as we did before, right? So, we would have expected the secondary current to be double the primary current. The reason for this difference is the magnetizing current. So let me go and have a look. If we go back to the code, we'll see that we have simulated a magnetizing current, right? We have simulated this magnetizing current. Now, the magnetizing current is the current which will be drawn even when there is no load connected. So for example, in this circuit, if I were to make this load very large, right, extremely large, such that the current were negligible, in that case, there would still be a current flowing in the primary. This current flowing in the primary is the magnetizing current that the transformer draws from the energy source to sustain the magnetic field, right? This is always going to be drawn. Now, if we have a look at our load, so let me just go back to the edged circuit parameters and have a look at the load. We will see that this load is quite large, right? It's a 100 ampere load, which means that the current is extremely small, and that is precisely the reason why we see this ratio to be very different. The reason is simple. Most of the current that is flowing in the primary is actually the magnetizing current, right? The load is very low, and therefore the load current component in the transformer is extremely low. The way to solve this is pretty simple. All we have to do is, this is just how it is. There's nothing to solve. We just have to, if we increase the load, we will see that this ratio becomes almost the same, right? So with this, let me go and simulate that last case of a heavier load. Let me increase this. So let me increase this to around 5 ohms, and let me increase the load to around 0.1 or 0.1, something like that. Yeah. And let me go back and let me stop the simulation, and I will run the simulation again, and we see there is no error, so we are okay. Let me click on the winding voltages and let me click on the transformer currents. So the winding voltages have unfortunately become infinite, right? Now this is a case again of instability. So it does appear like as if we are pushing the boundaries of instability, and for this the only solution I would say is we need to decrease our time step of simulation. So let's go over and do that. Let's go again, check if there's an error. There is none. Let me before check if at least it has produced a result. We still have instability. And as you can see, this kind of instability is a little difficult to solve. One other reason for this kind of instability is the way we have solved it. If we use a higher order solver, it would be a little more accurate. Let me run the simulation again. As always, check if there's an error. There is none. And let's click on the winding voltages again. I hope this time we do have instability. No, we don't. So this is something that we need to solve, and I think we need to solve it fairly conclusively. So the only way to solve this is to actually think of ways in which we can solve this equation in a better manner, right? Now I will stop this video now because it's already getting a bit too long. In the next video we will examine a more rigorous way to solve this so as to achieve a more stable result. So as before, if you have any doubts, please do post in the comments or send me an email or message me on social media, whichever is your preference. In the next lecture, we will continue with this and try to solve this instability problem. So, thank you so much for watching and see you soon. Goodbye for now.